put it in the middle, but you can choose which way to go. Hi, good morning, everybody. Thank you for coming out on a nice Monday, which will be rainy soon. Let me remind you, this Friday will be test number 1. I've already talked about the chapters that we'll cover, 1, 2, 3, and Appendix A2 and A4. If you haven't bought one yet, you'll need a calculator, one that does scientific notation. I have a good one in the syllabus. You can get it just about anywhere for under $15. You get it now if you don't have it, and practice with it. Also, if you're not sure, see me during lab this week. This week's lab, we will be going through problem set for Chapter 3, so I hope you have tried that out before I do it. I think that brings us up to date, other than, anybody think about the fact that when you were walking in, did you all feel the wind in your face? I did. And did you think about that's molecules of nitrogen and oxygen hitting you real hard at a high speed? It is. That's why I always laugh when people say I hate chemistry. They don't hate chemistry, they hate the way it was taught to them. Hopefully I'm doing a better job. All right. Last Friday, I was talking about covalent bonds. Remember, covalent bonds are sharing pairs of electrons. I started talking about different types of covalent bonds. And the first type is a single bond. Remember, this material will be on test 2, not test 1. Start off the week being subtle again. And the different types of covalent bonds are single bond. And a single bond involves one pair of electrons. Remember, a pair is 2. And then there's a double bond, 2 pairs of electrons. And a triple bond, 3 pairs of electrons. Remember, they're sharing between 2 atoms. Now, last Friday, I sort of speeded through this. Let me go back and do it again at normal speed. And that is, how do you draw the Lewis structure for a following? Hold on 1 second. This pen is. Sometime in the future, in a piece of paper I'd like to hand out in this room, and it says 3 points each, draw the Lewis structure for, and I give you nitrogen gas, N2. What do? Well, first of all, you look at the periodic table at the back of the test. Every test I'll give you, and by the way, if you want, you can look on lectures folder, and you'll see the actual information, important information. Won't have the periodic table. I think I've scanned this, maybe. tomorrow I'll have a chance. Now, if we look at the periodic table, we look at nitrogen, and nitrogen, you look at the number at the top. Remember, Lewis structures are only valence electrons. Valence electrons are the outermost electrons of an atom. And therefore, if we look at nitrogen, at top, it has 5 valence electrons. So if I do one nitrogen, do the Lewis structure for the atom, and 1 dot on each side, and then you double up. And I have 5. 1, 2 nitrogens. Same thing, you're not seeing double. But anyways, well, you are actually, there are 2 of them up there. I lied to you. Oops. But anyways, each one of these has 3 unpaired electrons. And this nitrogen turns to that one and says, I've got 3 unpaired electrons. You have 3 unpaired electrons. Let's share and make a covalent bond. What kind? Well, let's look. These are non-bonding electrons. They're not involved. They're already a pair. This one shares. This one shares. And the outer one shares. And now we have nitrogen gas. Now, I've talked about the octet rule. All atoms want to have 8 valence electrons. And if we look at this nitrogen, and I talked to you last week, I have magic organic chemistry hands. I covered that one, and how many electrons do you see? 2, 4, 6, 8. That's good. And if I go over here and use, I'm ambidextrous to both hands, or magic organic chemistry hands, 2, 4, 6, 8. So both have an octet. The one exception is hydrogen, which octet is 2. And now the question is, what kind of covalent bond is between the 2 nitrogens? Good question, thank you. Well, you count pairs of electrons. 1 pair, 2 pair, 3 pairs. And if we come over here, because someone was nice enough to put a table on the board for us, whoever that person is, I'll thank them later, and we have 3 pair electrons, triple bond. So between nitrogen, 2 atoms, what kind of bond exists? A triple bond. And when you were coming in here this morning and hitting the face with the wind, most of the wind is made up of nitrogen gas, so you were getting slammed by a triple bond. Bet you didn't think of that. I did, because I knew I was going to talk about it. And since you know I'd like to share the fun, why don't you try doing the Lewis structure for oxygen? Now I'll help you out. The first thing you have to know is where's oxygen? Right there. Look on top, how many valence electrons, and the answer is 6. On a test, I won't do this, you have to know that, but today, I will help you out. And there you have 6 valence electrons. Why don't you try and do the Lewis structure for oxygen gas? Because that was also hitting you in the face today. For those who have lab tomorrow, don't forget to bring your lab. That's what you did last week. Don't forget your to-do list. Don't forget your goggles. And don't forget, you can't wear any leggings, blue jeans, or other types of pants with fashion cuts in them. Or big holes. Quick commercial from Dr. White. Thank you for making me a YouTube star. I've been keeping up. All the lectures are on YouTube, and the CHEMI, I guess you pronounce it, 1105 YouTube channel of mine. All right, when you're done, don't forget to look up and smile. All right, I think everybody's done. Well, see electrons still going down. All right, looks like everybody's done. How do you do this? 2 oxygens. I'll do the one at a time. 6 valence electrons. 1, 2, 3, 4. Organic chemists like to put the next 2 top and bottom. Doesn't matter which side you put them on. I'm an organic chemist and I don't break good habits. The other oxygen, same thing. Now, if you look at these, this part you don't have to put on the test, but it shows you the thought process and how to put down the right answer. This oxygen says, oh look, I have 2 unpaired electrons. It says to that oxygen, you have 2 unpaired electrons. Let's share both, and we'll have 2 pairs. And they do. Both pairs of electrons already there are still there. Those are called non-bonding. First pair, and then this and this. Second pair, I'll circle them. How many pairs? Ooh, this is getting tough. 2. And if we come over here to this nice table some anonymous person put on the board, we see 2 pairs of electrons, a double bond. So the next time you see a friend of yours inhaling and breathing, you can tell that friend, neighbor, loved one, guess what? You're inhaling oxygen gas and it has a double bond. Don't people don't like reading chemistry when they're breathing. But anyways, you're doing it right now. And the nitrogen you're also inhaling, because air is 80% nitrogen, 20% oxygen, has a triple bond. So you're inhaling, and when you walk out and feel the wind, you're being pelted by double and triple bonds. And you'll find out when you take other chemistry like organic, double and triple bonds play an important role in our daily life. Let's do another one, but this you've got to figure out. I'll let you try it. What would be the Lewis structure for CH4? This is called methane. You also know it as natural gas. It's what you use to cook with, heat your house, and also most of us in northern Illinois use it to heat the water so you can have it when you wash your hands. It's not only cold water, if you decide to, you can use hot water. Now, how do you proceed? And I'm going to help you out. Carbon, how many valence electrons? Look at the number at top, 4. Hydrogen, look at the top, 1 valence electron. And I'll tell you, the carbon is in the center, and the 4 hydrogens are on each side. One on each. Alpha. Those who came in late, sign sheet is here. Make sure you sign in before you walk out. Oh, it warms my heart to see everybody doing chemistry. Thank you. Not see anybody in serious pain either. That's a good thing. Remember, carbon is the center, surrounded by hydrogen. Give you 7.65 more seconds. I got a slow clock today. All right, let's take a look at this. How do you do this? How do you draw the Lewis structure for methane, which you also know as natural gas? Carbon, 4 valence electrons. That wasn't hard. Each hydrogen has 1 valence electron. I can clean it up and make it look like this. This carbon has 1 valence electron. This hydrogen has 1. They said, how about let's share our electrons and make a pair. And 1 pair is a single bond. And it does that. And it does it each side. Now, hydrogen, the octet is an exception, is 2. So once again, my magic chemistry hands, and notice that hydrogen has 2 electrons. It's happy. That one does, that one does, that one does. Now for the hard part, I need both hands. And that is, does carbon have an octet, 8 valence electron? Let's find out. Count the dots. 2, 4, 6, 8. It does. And this is the actual structure of methane. This is hydrogen cyanide. I'll let you try this one on your own. Hydrogen has 1 valence electron. Carbon, 4 valence electrons, look on top. And nitrogen, 5 valence electrons. In this molecule, and I'll help you out now, but on a test I won't, the carbon is in the center. One side has nitrogen, the other has hydrogen. By the way, this is a very dangerous poison, but it's a good example for valence electron. All right, anybody need more time? Going once, twice, let's do it. All right, we know hydrogen has 1 valence electron. And carbon has 4 valence electrons. And nitrogen has 5 valence electrons. And now, how do we put this all together? I helped you out. Carbon is in the center. First of all, how did I get this? By the numbers in the top of the column of the periodic table. Well, this hydrogen says, I've got an electron. Carbon, you've got an unpaired electron. Let's share them. And it forms what kind of bond? Look over there. one pair of electron, a single carbon is a single bond. Now, that's this electron. Carbon looks over at nitrogen and says, I have 1, 2, 3 unpaired electrons. Nitrogen, you have 1, 2, 3 pair of electrons. Let's share them, and we'll make 3 pairs of electrons. What kind of bond is when you have 3 pairs of electrons? A triple bond. And therefore they do. And the non-bonding electrons on nitrogen are still there. Now, true test is, does each atom have an octet? Remember, hydrogen's octet is 2. It's the one exception. So I use my magic chemistry hand. Oh look, 2 valence electrons. Hydrogen has its octet. Let's look at nitrogen. 2, 4, 6, 8. It has an octet. And now, because I'm ambidextrous, I can use this hand. And we look at nitrogen, 2, 4, 6, plus the 2 non-bonding electrons, 8. So everybody has their octet. Remember, hydrogen's octet is 2, so everybody's happy. And let me do this one. I did earlier with sodium hydroxide when you have a polyatomic ion. And let's take a look at this. This is sodium cyanide. And it also can be made into a poison. I won't teach you how. But let's look at this. The first thing I see is a sodium. And it's an alkali metal. If we look over at the periodic table, the first column, the alkali metals, and the second column, the alkaline earth metals, always form ions. I know of no exception where they're in a covalent bond. Never. And I can say that because over the years I've asked other chemists, can you come up with an example? No, because there is none. Therefore, sodium, what ion does it form? We've gone through this. You'll lose 1 electron to get the same number of electrons as neon, 10. It will still have 11 protons, so it'll form a +1 ion. So I'm going to do that immediately because it's never going to be in a covalent bond. Everybody with me on that? All right, now, carbon has 4 valence electrons. Nitrogen has 5 valence electrons. And the carbon will have 3 valence electrons that it can share with the 3 valence electrons of nitrogen. It's got a non-bonding pair. Notice carbon has 4 valence electrons. Nitrogen has its 5, we just did that. And now if I look at this and I say, oh, all right, let's check. Sodium, because it gave up an electron, has a positive charge, has the same number of electrons as neon, which means it has an octet, 8 valence electrons. Now, if I come over here and look at nitrogen, I see 2, 4, 6, 8. Wow, things are looking good. 8 valence electrons. Now let's do carbon, because I think I'm done. 2, 4, 6, 7. That's not an octet. What's wrong? Well, we forgot. Where did the electron, the sodium cation, go? It gave up one. This isn't floating around. No, it's not. I can see that it's going. It goes here. It transfers this. And now this has an extra electron. So between the sodium and this is called the cyanide anide, there's a ionic bond. And between the carbon and nitrogen in the cyanide anion, which is a polyatomic anion, you have a negative a triple bond between the carbon and nitrogen. And that's how that works. Let's go through it again. As soon as I see an alkali metal here, first column, or alkaline earth, second column, it's going to transfer cation, always. Therefore, this one, as we learned how to figure out charges, remember, once you learn one in a column, you know them all. The first column is always a plus charge. We'll do that. Now, the carbon has 5 valence electrons, and first of all, there wasn't one here. Let's do this for the time being. Our carbon has 4. There go 4. Nitrogen has 5. There are 4 unpaired. This has 3, so it forms 3 pairs. And then this electron from here goes there, so everybody has an octet, and this has a negative charge. And that's how you do it. Now we'll do some more in the practice problems, but I'd like to move ahead. Now let's do one more. I lied. Why don't you try this one? This one, the carbon is in the center. On each side of the carbon is an oxygen. And this only has covalent bonds. I'll help you out on a test. I won't do that. I'm up to about 52.5% of your names this week. I'll be working on learning your names in lab again to bring that even higher. And hopefully within a week or two, I'll know all your names and you'll no longer be anonymous students. Some of you are still working. Years ago when we were in the other building before they built this building, we had white blackboards on the sides and the front. I used to make students go to the blackboard to do problems I put up there. So I realized they'd rather pull their teeth out with pliers than go to the blackboard, so I stopped that. That wasn't nice. Oh, they hated it. All right, let's do this. How do we do this? We look at oxygen, 6 valence electrons. Carbon, 4 valence electrons. Carbon here looks at that oxygen and says, oh look, you have 2 unpaired electrons, I have 2, let's share. And form 2 pair of electrons, double bond. This has still 2 unpaired electrons, looks at that oxygen and says, hey, I have 2 unpaired electrons, you do, let's share, and they do. And they form a double bond. And carbon dioxide, CO2, they're 2 double bonds. A double bond between this carbon and oxygen, between this one. And let's find out, let's check the octet rule. If I cover all this, that oxygen has 2, 4, 6, 8 carbon, 8 valence electrons. And if I go this side, 2, 4, 6, 8, octet, and now the hard part, hold on, let's see if I'm up to it. I am 2, 4, 6, 8. So carbon dioxide has this Lewis structure. How many of you have ever seen the bubbles in a glass of pop, beer, or sparkling wine or champagne? Guess what? That's CO2, which has 2 double bonds. How many of you have ever burped or had a friend in your presence burp? Most of the burp coming out is your body getting rid of carbon dioxide. So next time you see a friend drinking pop or burping, you can tell them, you know, the gas you just burped or the bubbles in there is CO2 with 2 double bonds. People don't like hearing chemistry when they're burping. All right, click. The next couple of slides, the switch is off. Will this be on a test? But it's good background information. Molecules are not straight across, all of them. They have shapes. They exist in 3 dimensions, just like you, me, or this eraser or pen is in 3 dimensions. Now, someone came along with the Vesper theory. Next slide, I have what that means. To understand how molecules interact, the electrons really in a molecule, the valence electrons, to cause the shape of molecule. Now, switch is still off. Vesper stands for valence electron pair repulsion theory. I forgot what the S stands for, but anyways, and it tells you how a molecule is shaped based on separating the valence electrons as far away. Electrons have a negative charge. The closer you bring them together, pairs of them, the farther apart they want to be. Anybody here ever play with a magnet? That's really depressing. I have a whole collection of, my father started giving me magnets when I was about 5 or 6, because he liked them too. If you ever take 2 magnets with the same poles, say like this, north and north, and you bring them together, they'll repulse, push away. It's fun when you have heavy-duty magnets and you do that, it's fun. And when they're opposite, they go click. Well, electrons are the same way. And the valence electron pair repulsion theory is based on the fact that atoms, pairs of atoms, want to be as far apart from other electrons of other atoms. And switch is still off. Certain molecules have certain shape. Methane is tetrahedral, ammonia is trigonal pyramidal, and water is not straight across, it's bent like this. And that has significant implications on how those molecules react with other molecules, like in your body. We won't go into that in this class. And let's just do something real quick. Oh, it stands for valence shell. That's what the S is. I left them off. Let's look at a water molecule real quick. I just drawn Lewis structure, looks like this, but you have these electrons wanting to be as far away from this and those, and the way they do that is by having what's called a bend, like right here. And if you think of the oxygen in the center, the hydrogens, the white balls, that's where the only shape where you get the electrons is far apart, including the non-bonding electrons. And that has implications, like I said, in how things react. Carbon methane, the center red is carbon, the four white balls are hydrogens, and there again, this is the shape. And this tetrahedral shape affects the way things are in your body, like your hormones. Hormones are steroids, which are organic molecules. Also, different foods you eat, like carbohydrates, fats and oils, protein, are all affected by the shape of carbon in what's called single bonds tetrahedral. That won't be on the test, but it's good to know. And now you know. Another thing I'd like to talk about, switches off now, but I'll come back to this later on, is called electronegativity. And electronegativity is the ability of an electron to attract electrons to itself. If I'm, say, hydrogen and oxygen, they're sharing a pair of electrons. But if I'm stronger than the other atom, I can say, let's share them, but share them closer to me. It's like when you were little and you had an older sister and you're out in a rainstorm and you had one umbrella that you shared, and she shared it closer over to her. You sort of stayed dry, but not really. Don't tell my sister I told that story. And so that's electronegativity. Now, if we look at the periodic table over here, electronegativity increases this way from left to right, and increases this way going up. Fluorine and oxygen are two of the most electronegative. In other words, they're big and strong. And what happens in water when that's not being equally shared is what's called a nonpolar covalent bond. And that just means the switch is off on this line. It's not being equal, and you can have polar. And what really happens is dipole. Di in chemistry means two poles, polarity. And in real life, and this plays an important role I'll talk about more, water really looks like this. And I'll draw it sort of. Now, for those of you who know math, delta, the Greek letter, capital delta, means difference. It's also in chemistry. Difference. One thing subtracted or just different. Because there's a slight charge here, chemists got cute and said, well, we'll use lowercase delta. If you know your Greek alphabet, you don't have to. And we'll make that little difference. So there's this very slight negative charge because of the difference in electronegativities, how strong an atom can keep its electrons closer to it, and makes it slightly positive. Well, it turns out if I have two water molecules, there's a slight electrical, we call that Coulombic attraction, that holds molecules of water together. And we have a special name for that. It's not a true bond, but they still call it a hydrogen bond. And this affects a lot of the physical properties of molecules or substances with hydrogen bonds. And one of the most important things, everybody see the stuff in the bottle? It's water. And what is it? It's a liquid. If you look at other molecules with the same molecular weight, at this temperature right now in this room, they're all gas. Water should be a gas. It's not. Why? Because of hydrogen bonding. And think about our planet. How would life evolve on this planet if water was a gas now? You wouldn't have blood the way it is. You wouldn't be the same body you're in now, because water would be a gas. And think about all the things in your body, your life is evolved because water is a liquid. So, this is an important aspect of this dipole, and another molecule that does that is ammonia. And with that, I'm done with this chapter. Now we can move on to the next chapter. But first, I'm going to have some water, which is a liquid because of hydrogen bonding. Again, this material will be on test 2, not 1. Don't forget, test 1 is this Friday. If you don't have a calculator, go out and get one. And I try and follow what's in our book, even though we don't use the book. I cut that out of the video. But anyways, next chapter is called Chemical Accounting. By the way, my mother and sister were both accountants. And I didn't want to be an accountant. I wanted to be a chemist. So I was. Chemical change. We talk about chemistry. Important thing is chemical change. And I will never ask you what's the chemical change on a test. But it's good to know when an original substance is converted to new substance, it has different composition, new chemical and physical properties. And therefore, if I were to step on the gas of my car, in your car engine, the gasoline undergoes a chemical change, and it changes from the chemical it is when you buy the gasoline to something different that comes out of your tailpipe of your car. And that's undergoing a chemical change. And another way of saying that, change, again, I'm never going to ask you this, change during a chemical reaction, original substance changed to new substance with different physical, I should have put down, chemical properties. This one, you should know, click, switches on. We talked about it last week in lab, but now in lecture. How do you know you have a chemical change? There are 4 things. The first one is a change in color. If you mix 2 things together and they're clear and all of a sudden now you have orange, guess what? You have a chemical change. Or if you mix one thing that's red with another thing that's clear and it changes to purple or green, you've got a chemical change. So color indicates a chemical change. The next thing, formation of a gas, which you can see as bubbles. And if you see bubbles form when you mix 2 things together, that's usually a good indication of a chemical change, which you did see last week. Hopefully you did. Next one is if you mix, say, for example, 2 clear liquids together, and all of a sudden you see a solid in there, which we call precipitate, fancy words you're learning in my class, that's an indication of a chemical change, which you also saw last week in lab. Wow. And remember I talked about the snow globe, or the paperweight with the snowman. If you shake it up, the chemists will say, look at the precipitate in there. Well, it's not really a chemical change, but when you see a solid form, we call it precipitate. And the last one is a change in temperature. And if something gets cold when you mix 2 things together, or hotter, that's a change in temperature, meaning a chemical reaction has occurred. How many of you are familiar with those packs you see when someone sprains their ankle? They take it, go like this, shake it up, and all of a sudden it's real cold. Guess what's happening in there? You're breaking something and mixing, actually it's called ammonium chloride with water, and it's undergoing a chemical change. And that's why it gets cold. Now, when we talk about a chemical change, and I will never ask you what's a chemical equation, but I will let you know what it is because I'll use that term in class. It's a written statement that uses symbols, chemical the elements' formulas, or symbols, and formulas instead of words to describe a change that occurs in a chemical reaction. So a chemical equation uses symbols to indicate a chemical reaction. Let's show one. I went through this in lab, but now that I'm doing it in lecture, I can put it on the test. Hint. But anyways, you should know the following. This is a simple chemical equation. We use an arrow. The base of the arrow, first of all, plus sign is the same as the word and therefore this is B and A and B react together. And these are called the reactants. Work in the chemical industry like I have most of my life. We also call them starting materials. The more likely, I'll probably call them starting materials. You should know both. At the head of the arrow, we're making C. When we mix A and B together, the chemical equation tells us the head of the arrow, what you're making. And we call this the product or products if there's more than one. And that's the same for academic or industry. Now, when you're writing a chemical equation, let's go through this again. Base of the arrow, A and B, plus side, and you could have also plus D over here. I didn't, but that would also mean you're making two things, not one. These are called the reactants. Or sometimes I'll use starting materials. At the head of the arrow are the product or products. Now, when you write down a chemical equation, there are certain things you should always do. I'll never ask this on a test, but these are understood by chemists that you should do this. And the first thing you should always do is use the correct formula for the reactants. Notice I have starting materials. And they're always written on the left side. If you're putting down water, you don't put down H5O7 because that's not water, it's H2O. The correct formula of the products, if you're making CO2, carbon dioxide, you don't put down C7O20, that's not CO2. You put down the correct, and it's always written on the right side, in case you forgot. Right, left, oh, I got it correct. God, I'm on a winning streak. And like I've already mentioned, the reactants and products are separated by an arrow, and the plus sign separates different compounds, and think of it as an and. And I'm going to let you out a whole 5 seconds early. For those who have labs tomorrow, please be on time. Don't forget all the stuff you're supposed to bring, and I'll see you then. We'll go through chapter 3 problems.